Hello and welcome to a new module on derivatives. In this session, we will revisit the definition of derivatives, explore the connection between the slope of the tangent line and derivatives, and work through derivative calculations. It's important to note that some prerequisites are required, including an understanding of limits, mathematical notation, and basic mathematical operations. Let's start by reviewing when a function is said to be derivable at a point. We say that a function f, a real function, given a point x sub 0 belonging to the reals, f is said to be derivable at that point if the limit that you are seeing here on the screen exists. It can be calculated. The value of this limit is referred to as the derivative of f at x sub 0, which we symbolize as f prime of x sub 0. We can extend this concept to determine if a function is differentiable within a specific set. We can identify when it's differentiable at a single point, and a function is considered differentiable within a particular set when it is differentiable at every point within that set. Let's briefly review the expression y equal to mx plus n, which represents a line with the slope denoted by m and the ordinate at the origin denoted by n. This is the general equation of a line. We will use it shortly, so I wanted to review it. Remember that m corresponds to the slope and n corresponds to the ordinate at the origin. Let's begin by discussing what a secant line is. A secant line is a line that intersects the graph of a function at two distinct points. Consider a function f of x and its graph, which represents the set of all pairs in the form x, f of x, where x belongs to the domain of the function. We want to construct a secant line that passes through 2 points, which we will call a, f of a, and b, f of b. These 2 points are specific points on the graph. To construct a line that passes through these 2 points, we use the general equation of a line and ensure it goes through the points a, f of a, and b, f of b. I've used parameters a and b instead of specific numbers to keep it general, but we can work with numerical examples later if you prefer. Let's determine the values of m and n, which is my objective. As a reminder, the equation of the line is y equal to mx plus n, where m represents the slope and n represents ordinate at the origin. I aim to make this line pass through the 2 specified points, a, f of a, and b, f of b. To achieve this, we need to set up the following system of equations. I substitute y in this general equation with f of a, which represents the value of the function for that particular value of a. I substitute a for x, as you can see here. F of a is equal to m times a plus n. This equation results from substituting y with f of a and x with a. I am specifying that this line, for which I don't have the values of m and n, must pass through the point a, f of a. I'm applying the same requirement to b, f of b. Note that I'm substituting y for f of b and x for b. What is the purpose of this equation? It is necessary for this line to pass through the point f of b, b. A line can always be defined by 2 points. Consequently, this system is a determinate and compatible one that can be solved in any preferred manner. It might appear a bit unusual, but it's important to keep in mind 2 key aspects. A, b, f of a, and f of b are values that you should already have, while m and n are the variables representing the unknowns. Even though it may seem like everything here is unknown, that's not the case. A and b are known quantities, and f of a and f of b are also known. The only variables to solve for are m and n. How can I go about solving a system of 2 equations with 2 unknowns? There are various methods available, and I'm open to any approach you prefer, whether it's substitution, elimination, or another technique. I'm opting for a somewhat unconventional method, Cramer's method, which I'm sure you're familiar with, even though it's not the traditional choice. This system is determinate and compatible and can be easily handled. According to Cramer's formula, the parameter m is determined by these 2 determinants. The determinant f of a, 1, f of b, 1 divided by the determinant of a, 1, b, 1. It is the determinant 2 by 2. I think you all know how to calculate it. It is f of a times 1 minus f of b times 1. Observe that the order is reversed here, and I also made a corresponding modification below. In fact, I applied a slight manipulation. The determinant of a, 1, b, 1, does not yield b minus a. It gives a minus b. Likewise, above, I obtain f of a minus f of b. They are indeed reversed. What I've done is flip both of them and eliminate the 2 negative signs that were present. I trust you grasp it. It's not overly complex, and in fact, if I were to reverse it, nothing would change. As for n, in accordance with Cramer's formula, It corresponds to another 2 by 2 determinant. Upon solving it, you arrive at this particular formula, which is also easy to verify. I've also adjusted a sign here. With this, I determine the slope and the y-intercept of the secant line. In other words, I establish a secant line that intersects the points A, f of A, and B, f of B. The expression for the slope is written this way in the hope that it reminds you of something. All right, do you remember this? It may ring a bell from a previous session. However, if it's not clear yet, let's make a simple notation change. We'll refer to A and f of A as x sub 0 and f x sub 0 respectively. We'll call B by x, which makes B and f of B become x and f of x. With this slight notation change, the slope of the secant line looks like this. It should look familiar now. Let's rewind a few seconds to the beginning for a quick recap. Doesn't that quotient seem familiar? Yes, indeed, it's the one we used to calculate the derivative. Let's go back to where we were. This, actually, in other sessions, we have referred to it as the average speed. In this case, it is the slope of the secant line. One example with numbers. Let's consider the function f of x equal to 1/3 of x cubed minus 3/2 times x squared plus 2x plus 1. This problem may seem to be complicated due to the fractions, but in reality, they won't pose any difficulties when we differentiate this function. Let's start by selecting any 2 points. I've chosen the points 0, f of 0 and 3, f of 3. These points correspond to 0, f of 0 and 3, f of 3. Calculating f of 0 is straightforward. You simply plug 0 into the function and you'll get 1. Therefore, the first point is 0, 1. To find f of 3, you follow the same process. By substituting 3 into the function, you obtain 5/2, which is approximately 2.5. So the second point is 3, 2.5, and the first one was 0, 1. As you can observe, these are the points. The tangent line, which we derive using the previously discussed formulas, is this one. By substituting b with 3 and a with 0, we obtain this secant line. Notably, this secant line traverses the specific points I aimed for, passing through both of them. Although it may intersect the function at additional points, the second line I've defined essentially intersects at these 2 specific locations. The possibility of multiple intersections is evident in this example. What does this have to do with the tangent line, and how are we going to define a tangent line? The definition we will employ is as follows. We consider the secant line, such as the one shown here, for example. Then we fix a point, assuming that it's at x sub 3. This point will be denoted as x sub 0 now. What I'm going to do is the following. Leaving the first point fixed, let's say it's 3, and taking values of x that get closer and closer to x sub 0, we obtain a collection of secant lines that tend toward another line. The line, which is the limit of all those secant lines, is what we are going to call the tangent line. And how do we calculate its slope? We achieve this by taking values of x that get closer and closer to x sub 0, essentially approaching x to x sub 0 step by step. What we are essentially doing is taking a limit. Therefore, the slope of the tangent line is something we already know. Does it sound familiar to you? We defined it in the first slide. Actually, that's the derivative of the function at the point x sub 0. Very important, it's not always possible to calculate certain lines. What I want to emphasize at this moment is that if this limit is infinite and the function is continuous at x sub 0, then we have a vertical tangent line. Sometimes it might seem that the tangent line doesn't exist, but it does exist, and in some cases, it's simply vertical. A note on this, I emphasize that we are going to see that we have a quotient, which involves a limit of secant lines, and this limit gives us a tangent line. The slope of the tangent line is the derivative of the function at that specific point. This is the key information for today. How are we going to calculate the tangent line? We won't need to use everything we've covered so far, as we know the limit in this context is the derivative. So how do we calculate the tangent line to the graph of a function f of x at a point x sub 0 and f of x sub 0? We will utilize the following expression, this formula here. It provides the means to calculate the tangent line. All you have to do is evaluate the function at the point where you want to determine the tangent line and find the derivative of the function. And then substitute x with x sub 0 to determine the slope of the tangent line. Simply take x minus x sub 0. You already know x sub 0. You know everything you need to calculate this line. By the way, while we're here, let's also define what the normal line is. The normal line is the line that's perpendicular to the tangent line. So, how do you calculate that? It's very straightforward. You simply need to change the slope of that line. If it's like this, all we need to do is adjust the slope to make it like this. How do you do that? You use the formula f of x minus 1 divided by f prime of x sub 0 multiplied by x minus x sub 0. The only change you make is replacing f prime of x sub 0 with minus 1 divided by f prime of x sub 0. Before we conclude, I'd like to review what we've covered so far. It consists of the following. See how secant lines work. I'm going to open the Mathematica program where I've prepared a demonstration of how secant lines work. This is the same example I showed earlier in the presentation. The function 1/3 of x cubed minus 3 halves of x squared plus 2x plus 1 is represented in blue, and in red I've represented the secant line. What is the secant line approaching? If I take x sub 0, the fixed point is 3. This point will remain fixed, and I'll bring this point closer and closer to 3, gradually moving it until it nearly coincides with 3. At this point, how will the secant line change? In the following manner, let me place it here in the presentation. Observe how the point is shifting. The secant line is adjusting its position until it comes to a halt just at the last moment, where it coincides with the tangent line. I'm going to adjust the point on the tangent line. I'm moving it. Let's set it at 2.9. What you'll notice now is that this is essentially the tangent line. I'm going to adjust it slightly a few more times, and this line here is what we call the tangent line. I could have approached it from the other side as well without any problem. What happens if now I approach from above 3 and go towards 3? You see, I get the same tangent line. The point is moving from 4 to 3, and the tangent line in both cases is exactly the same. This is what's happening. The important thing for today is that the slope of this tangent line in the end is the derivative of the function at that point. Let's return to the presentation. We were at this point. One more example. Earlier, I mentioned that sometimes the tangent line does not exist. One case in which it does not exist is the following. The absolute value of x. This value is defined as x when x is positive and minus x when x is negative. In other words, the absolute value of minus 3 is minus minus 3, which equals 3, because negating a negative number makes it positive. This is how we've always handled absolute values. If the value is already positive, we leave it unchanged, but if it's negative, we transform the negative sign into a positive one, which is equivalent to adding another negative sign to cancel it out. This is the mathematical definition of the absolute value. The absolute value has a graph like this, which ends in a peak. It's important to note that there is a tangent line at all points of this function. Except at 0, at that peak, there is no tangent line. How and why? If you apply the definition, you have to consider the limit in two parts, one from the right and one from the left. You will see that the limits from both sides do not coincide. That is to say, when the graph of the function has peaks, the function will not be differentiable. It is continuous. There is no doubt about that. In fact, I can draw it without lifting the pen from the paper, but it is not differentiable. You also have to consider that being differentiable is like a kind of smoothness condition. If it's differentiable, it means that it doesn't have peaks like this. The function is smooth. I hope that all of this has been helpful. Today we reviewed the concept of the secant line, tangent line, and briefly touched on the normal line. We discussed the relationship between the slope of the tangent line and the derivative, emphasizing that they are one and the same. The slope of the tangent line at a point is equivalent to the derivative of the function at that very point. Thank you very much for your attention.